Alright, so in this lesson we're going to talk about Hooke's law. Now, Hooke's law deals with, we're going to mainly look at springs, but it deals with any elastic material. And in an elastic material, let's go to the next slide. There we go. Okay, so we have stress and strain. Let me just talk about what these things are. So stress is an internal force that acts on surfaces within a body. Now, if that force causes the shape of the body to actually change, then that's called strain. Okay, now when we're dealing with springs, we're talking about normal stress. A normal stress is just when the force is perpendicular to the surface, as in this example right here. Don't know if you can see my mouse, but this example with a spring just pulling it down. Okay, however, you can have shear stress when the force is tangent to the surface, like this example with a textbook. Okay, but we're not going to talk about shear stress. We're not going to talk about strain. We're just going to talk about normal stress, and specifically on springs. Now again, spring is an elastic material, and there's a portion where Hooke's law is obeyed and a portion where it's not obeyed. Now I'm sure you've all dealt with say plastic bags. So you go grocery shopping, you have plastic bags, and it can stretch a little bit, and it just bounces back. However, if there's too much mass in your plastic bag, the weight pulling down on the bag causes it to stretch so much that it can't bounce back. It completely deforms the shape of the plastic bag. And that's a permanent deformation. That's happening over here. And if it keeps deforming, eventually it just snaps. Right? And that's when you have a fracture. So usually when we're in class and we're working with our actual springs, I give students a limit for how much weight they can put on a spring. And the reason for that is, well, previous students have put too much weight that causes the springs to be permanently deformed. I've never had a situation where they've actually fractured the spring, but I mean, it's also a possibility, and I don't want to have to purchase new ones. So in this course, we look at only normal stress, and specifically Hooke's law, which is in this region here of the elastic region. Okay? So it's all for the PowerPoint. We have an example, but there's only one example. So Hooke's law is based off of Robert Hooke. Robert Hooke was a British scientist at the same time as Newton. In fact, Hooke and Newton were arch enemies, arch nemesis. And the reason for that was when Newton was coming up with all of his great ideas on optics, his friend, I think it was Halley, his friend Halley, or Halley, Edward Halley, convinced him to publish his work on optics. And when he did that, Hooke was one of the scientists who was supposed to review it. And when he went to review it, he said, this is good, but I thought of it first. Right? And Newton doesn't like confrontation. He doesn't like putting himself out there. He just liked doing the science for the sake of science. He wasn't a very social person. And so he hated that, and he just went into recluse on his own. Right? And even though he came up with his ideas, was world-changing ideas on motion and forces and his Principia, calculus, all of that, he never published it. It wasn't until much, much, much later, till the debate on why planets orbit in ellipses, that Halley actually convinced Newton to publish all of his work and helped him do it as well. And again, Hooke tried to get his name put into Newton's book, saying that he helped Newton with all of his work, and Newton just absolutely refused that. And with good reason. Why would you? He didn't do anything. But Hooke was a very smart person. He came up with many, many different ideas. He came up with the iris diaphragm, which is used to adjust the light, cameras, for example. He came up with the artificial respirator. He came up with the compound microscope. He used the compound microscope to discover plant cells. So he was the first person to discover cells. So he's done a lot of work, and one of the work that he gets his name after is his work on elasticity. Okay, so this is why it's called Hooke's law. And Hooke's law is pretty much written like this: the force on an elastic equals to K times X. Well, we usually write plus or minus. I'll explain what that is later. Let me make this big now. Okay, so here's Hooke's law. The force on elastic is K times X. X is the displacement of that spring or elastic material from equilibrium. Okay, so let's say you just have a wall. Okay, and we have just a spring, and it's just sitting there in equilibrium. No force is acting on it. Okay, now let's call that then our X equal to 0 point, because that's our equilibrium. Now, if I were to compress it, or if I were to stretch it, well, I stretch it a certain distance x, or I compress it a certain distance x. And that is what our value is. Our distance or displacement from our equilibrium position. K is a spring or force constant, and it has units of newtons per meter. So we have different springs, right? We have springs that are very, very easy to stretch and springs that are very, very hard to stretch. If it's very, very hard to stretch, we have a greater spring constant. Right? More newtons required to stretch it 1 meter. All right, so where does the plus or minus come from? Well, let's say we just take a box here. Okay? Now, if I pull this in this direction, I'm applying a force on the spring. But then you can also think of it as the spring applying a force back on me, or back on the box, if you want to think. It doesn't matter, right? And it basically comes from action-reaction. What's the direction? Right? You get to choose, right? We've gone over this a lot. You get to choose which direction is positive, and then therefore this force will be positive or negative. So that's all that is. Nothing fancy. It's just the fact that it is a vector quantity. Okay. Okay, so with that, let's go back and do this problem. Here we have a student of mass 62 kilograms stands on an upholstered chair containing springs, each of force constant 2.4 times 10 to the 3 newtons per meter. All right, so we have a chair. There's a chair. Then we have 6 springs. 2, 3, 4, 5, 6. All of them have the same value, K. And it wants to know the compression in the spring when somebody sits. So when somebody sits on it, let's just look at this as a free body diagram. When somebody sits on it, you're going to have a downwards force of gravity, which is the weight of the person who is sitting on it. The springs are going to apply an equal but opposite force. Let's call it F. Your textbook uses X. That kind of makes me sound like I'm talking. I'm going to just do F squiggly. There we go. I like using X and Y for components, but you can use X if you want to. I mean, X does make sense. It is in one component. We can just call that the X component. But I'm ranting now. Anyways, so here's a free body diagram, and it's an equilibrium, so we know that the net force acting on the object is 0. You can choose a positive direction. Doesn't really matter. Let's choose up to be positive. So we have a positive spring force minus our gravity equals 0. All right, now that we have that, we can put in an equation. Well, the equation for gravity, that's easy. That's mg. We can even bring it to the other side and make it positive mg. Okay, remember, do not put in a negative for gravity. Right? This is the magnitude of the force. Right? You've already chosen the direction. So direction, magnitude, direction, magnitude. Since this is just the magnitude, do not throw a negative in there for gravity. Okay, because then you're going to get your directions all wrong. All right, so the spring force, well, it's kx, but there's 6 k's. So what do I do here? So on your sheet, there's 2 different examples. You can attach a spring, well, 2 springs together, either like this, side by side, on an object, or you can attach them one after the other, like that. Okay, this is the easy one. This one is in parallel, and so we just add them, right? So if this is K1 and this is K2, we can say our K equivalent is just K1 plus K2. However, in this case, if we have K1 and K2, we have to say 1 over K equivalent equals 1 over K1 plus 1 over K2. Right? In this case, they're all in parallel, so we just add them. And you get K plus K plus K, and in this case, all of them are the same, so we're just going to have 6K. So if we have K equivalent times X, that K equivalent is equal to 6K. Mg. And since we're solving for X, we're just going to divide both sides by 6K. You can plug in your mass. I don't think you have to change any units here. They give you kilograms and per meter. No, you don't have to change any units. So plug in all of your knowns and you'll get 0.042 meters, which is the same as if you want to put it in centimeters, 4.2 centimeters. Okay, hopefully everyone's okay with that lesson. Tomorrow we'll talk more about elastic potential energy.